All right, very good. Unfortunately, the next couple of sections of this presentation, the file was corrupted, and so we're going to have to do a voiceover on the slides and continue going. Our IT team tells us that those portions are simply not recoverable. But we're discussing samples and the fact that a sample has an inherent flaw associated with it. The uncertainty with a sample may be undefinable or it may be well defined. It just depends. But with regard to samples, what we can do is we can look at the sample as though it was a target, where the center of this target is the truth. This is the item that we're saying this is the truth. And we're going to collect samples, and those samples then are going to try to represent the truth. Now, sometimes the samples may be neither accurate nor precise, such as in this particular example. We see that there is considerable variation about the mean, and we're nowhere near the real target. In some cases, however, you may have good accuracy, but poor precision. And we see that quite frequently, for example, with, doing air monitoring in a factory, where we're pretty close to the right number, but the day-to-day variations are pretty significant. So we have good accuracy without precision. Excuse me. In some more rare cases, we have very good precision and very poor accuracy. This data set, however, is very, very useful, because if we have samples that are very tightly grouped, then that tells us that we have systematic error associated with it, and all we have to do is apply a correction factor and take those data, and that will get us down into the truth. That will be what we're looking for. Now, with regard to most of the folks that are running around collecting air samples for molds, this is what they think they are getting. They believe that they are getting accuracy and precision from a single sample. They are getting neither. The typical certified mold inspector or certified microbial consultant really has no idea of how to collect a sample or the limitations of the samples they're collecting, and they don't realize that their samples are virtually entirely useless. They have neither precision nor accuracy. So let's take a look at myths of sampling. Myth number one, samples represent the truth. The reality is that sampling is an exercise in uncertainty, and all samples are partially wrong. We just don't know to what extent those samples may be wrong without some further investigation. And it's the responsibility of the consultant to know the limitations of those samples and then place that information into correct perspective. Myth number two, we see this an awful lot, whereas the person collecting the samples, they think that the laboratory is going to interpret the data for them. And in some cases, we see some products out there like Mould Score or the ERMI or other proprietary products where the laboratory goes out on a limb and the laboratory tries to interpret the data. In every case that we've looked at, without exception, the laboratory's interpretation has been incorrect. And so one really should not expect the laboratory to do anything other than analyze the sample, give the data to the consultant, and then leave it up to the consultant's professional discretion and their data quality objectives to interpret that data. So when you get a lab report back or you see a lab report, you have to understand that the lab report contains only numbers. It does not contain data. It's the responsibility of the consultant to take those numbers and that information on that lab report and turn those into data. And they're going to turn that into data using data quality objectives. When we talk about precision, we know that every time we look at an analysis, and it doesn't matter whether it's a lead exposure on a construction site or maybe benzene exposures in a factory or whether it's a sample for airborne spores, we know that there is going to be two limits. There's, based on any one reported value, that there's going to be an upper confidence limit and a lower confidence limit, or also known as lower confidence interval, upper confidence interval. essentially when we get a number back from a laboratory, we know that it's not the truth. So now we have to calculate statistically that based on that number, how high could the concentration have been and how low the concentration could have been. Historically, industrial hygienists are going to calculate the upper confidence interval, and regulatory compliance personnel are going to calculate the lower confidence interval. But essentially, a reported value on a laboratory is a probable value, and it's up to the consultant to try to figure out then how high are those error bars? How far do they go? And what we see when we look at those kinds of variations, we see that those error bars can actually be huge. Now, this graphic, what we're looking at is this is aerosol spore data. It is from a building in Denver. And if we take a look at the samples, these samples were all collected in exactly the same manner throughout the day, starting at 9 a.m. and finishing at 5 p.m. And what we see is that the spore counts for the exact same area, collected in exactly the same way, changes wildly. So we have a low of about 100 spores per cubic meter of air at 9 a.m. and we have a high of about 2,000 spores per cubic meter at 10:45. And when we look at that, we find that the data are not normally distributed. That is to say, it is not a Gaussian distribution. More typically, what we see with spore counts is a log normal distribution, meaning that there is a huge variation about the mean and it's skewed in one direction. One can kind of generally estimate what the geometric standard deviation is, or the log normal distribution is, by taking the log of the data and then just looking at the Gaussian distribution on that. And if it is a Gaussian distribution, if the log transform data are Gaussian, then one can assume that it's going to be a log normal distribution. There are better ways to do it, but that's a pretty quick and easy way to do it. And so what we find is if we take a look at the geometric standard deviation, it's really quite large. And therefore, based on one sample, if we had a consultant go in as a certified mold inspector, goes in and collects a sample at 9 a.m., he's going to come away with a very different impression of the spore loading than if he takes the sample at 10:45. Now, what we know is that if we were to take samples every 3 minutes throughout the entire day, the spore concentrations are going to vary wildly from sample to sample to sample, even just over the course of a couple of minutes, never mind over the course of a couple of hours or days. So when we take a look at particular spatial distributions, or we take a look at temporal distributions, one of the things we're looking for is precision. How precise are these samples? And in this particular slide, what we're looking at is this is an experimental situation that I've set up on this particular, for a series of studies that I performed. And what I have is I have two aerosols that are only a matter of about 90 centimeters apart. And then I've got a N6, a stage 6 Anderson sampler in the center. And all of these are all activated at exactly the same time. And obviously the air is exactly the same time. One of the things that we did in this particular set of experiments was we wanted to make sure that we didn't end up with either stratification or end up with rarefied air. As these samplers collect the air, they're going to necessarily scrub out the spores that are present, and therefore in the small zone surrounding these, you're going to have essentially cleaner air. And so to make sure that that didn't happen under all circumstances when we had this set up, we were breaking up the stratification by ensuring good mixing within the study area. When we look at the data, what we find is that there is virtually no correlation. It is even with two exact samplers, two identical samplers, only 90 centimeters apart, run at exactly the same time, resulting in instantaneous collocates, we find that there's horrible correlation between them. You can't compare two aerosol samplers, and I'm not picking on aerosol, you do this with any kind of a spore trap, you're going to end up with essentially the same thing. But really, what it tells us is that your precision is so bad that you can't even you can't even compare two spore trap samples right next to each other. You're not even going to get close to having the same data. And so people think, well, I'm going to compare my sample in the kitchen with my sample in the living room, or my sample in the living room with the sample outside, you can't even compare two samples collected right next to each other in the same room at the same time. You won't even be able to compare those. Those two samples are going to be wildly different. And so to think that you can actually then turn around and collect a sample or two samples or three samples and use those for comparison, it's just fantasy. You're not going to be able to do it. It's just completely a myth. And so what we need to remember is that the number of samples that one would have to take within a building would be cost prohibitive. If you're going to try to figure out what the actual spore concentrations are, it would be cost prohibitive. And at the end of the day, the only thing that you would know is what was the mean concentration for that day. If you repeat the same process the next day or a day later, 2 days later, it's going to be completely different again. And so you have to ask yourself, why are you even doing this? Now, frequently we'll also see tape lifts. Tape lifts are collected by many consultants who don't understand the idea of a tape lift, as we've already discussed in a previous, in an earlier part of this discussion. Knowing the type of mold that might be present provides you with absolutely no information. You're not going to change your remediation processes based on what kind of mold it is. And so tape lifts don't quantify anything. For example, you might be able to go into a building, a 20-story building, and find one colony of mold the size of a U.S. penny. And if you take a tape lift off of that, the lab's going to tell you that there's millions of spores per square centimeter. Okay, fine. So there's millions of spores per square centimeter in a single colony the size of a penny in a 20-story building. What if that's the only colony present? Does that mean that the building has a mold problem? Of course not. And yet, that's exactly the argument that these certified mold guys try to make to frighten their victims, is they say, oh, look at this, I've got a laboratory result, and I took this tape lift, and look at, oh my gosh, there's billions of spores. This means billions of spores per square inch. Oh my gosh, this is horrible. Yeah, no, it's a colony, a single colony. It's the size of a dime or a penny. Big deal. Who cares? And so there's really nothing to be gained by tape lifts. Tape lifts cannot have precision because the tape lift is so selective already in its application that it would be extremely difficult to try to figure out any kind of statement of precision that may be associated with it. So what we're going to do now is we're going to play what's called the numbers game. We're going to look at accuracy of quantification. And to play the numbers game, let's go ahead and assume that we've got two air cell samplers, or Anderson or Burkhart, and they're collected from the same residence. And using the same equipment and the exact same spore types are present, meaning the profiles of the spore types are exactly the same, for the same sampling length of time and at the same flow rate, we have two samples. We have an outdoor sample of 1,233 spores per cubic meter of air, and we've got a bedroom sample of 2,283 spores per cubic meter of air. And we see this being done a lot with the certified mold inspectors, who say that, well, I collected an indoor sample, I collected an outdoor sample, and the indoor sample was higher than the outdoor sample, therefore the property has a mold problem. But based on these data, can we even say which sample represents the greater spore concentration in the air? Let's take a quick look. Let's play the numbers game. But before we do that, let's just refresh ourselves with a little bit of particle capture physics. What we know is that each of these types of samplers has what's known as a cut value, or a cut size, a D50. The D50 is that spore size for which the sampling device will capture 50% of that species present. And for the Zephon, we see that D50 is 2.3 micrometers when the temperature is 70 degrees F and you have a flow rate of 15 liters per minute. However, what we also can see then is that the capture characteristics are changing depending on both the temperature and on the flow rate. And so if you're collecting a sample inside at 70 and a sample outside at 23 degrees, you can't even if everything was exactly the same, you still wouldn't be capturing the same particle properties. You'd have something completely different. So we say, well, okay, is 2.3 micrometers important? Well, it is significantly important. Here we have the sizes of the particulates of the most common spore types.